Section 10.2, we're going to start looking at the calculus with our parametric curves. So the first thing we want to do is we want to touch on tangents. So again, we have our x is defined as f of t, y is defined as g of t. So traditionally, f goes with x, g goes with y. The slope of c at xy is, again, as usual, our first derivative. So to find this derivative dy over dx, we're going to have to do dy over dt, look at the y equation and take the derivative with respect to t, over, take a look at the x equation, take the derivative with respect to t, and that's where we're going to make sure that dx over dt is not equal to 0 because then we're undefined. Second derivative, a little bit different story. A lot of people get this confused as saying, oh, take the derivative of the top with respect to t for the y, take the derivative of the x equation with respect to t, and then do the derivative of the top and the bottom again. No, that is wrong. Okay, so please make sure you have this formula handy. To find the second derivative, yes, we are going to take the derivative of the first derivative on the top with respect to t. But on the bottom, it's the same dx over dt as it was for the first derivative. All right, so our dy over dt is our vertical velocity. Our dx over dt is our horizontal velocity. What does that mean to us? Well, your horizontal tangent line, when dy over dt is equal to 0, that means we're not moving up or down. Then we have a horizontal tangent. We just got to make sure that dx over dt doesn't equal 0 on the bottom, because then you have a 0 over 0 in indeterminate form. We don't want that. And if we want a vertical tangent, then our dx over dt is equal to 0, but at the same time, the numerator dy over dt cannot be 0. All right. Find the points of the curve where the tangent line is horizontal or vertical. So we need to find dy over dt. That's going to be 3t squared minus 6t. We got to set this equal to 0. Factor out the 3t. We get t equals 0 and 2. So at time of 0 and 2, we have a horizontal tangent. Our vertical tangent comes from dx over dt. Take the derivative of that, 3t squared minus 3, set that equal to 0. We get t squared minus 1 equals 0. We get t equals negative 1 and 1. So these are the 4 times where we have either horizontal and vertical tangents. So we're going to put those in our chart, crunch the numbers in for t, for x and y, and bam, there's my x's, bam, there's my y's. Now, of course, I got those really fast because I really did them in my calculator. And I also made the graph in the calculator because, as you can see with my points, there's only 3 points here, 2 and negative 2 repeats. That's really hard to figure out how I'm going to draw a curve with just 3 points. So when t is equal to negative 1, I'm at 2, negative 4. T equals 0, I'm at 0, 0. T equals 1, I'm at negative 2, 2. And at t equals 2, I'm back to 2, negative 4. So with my calculator assisting me, I have a good idea how to draw my curve. And the biggest thing is make sure you put your arrows in there so it's showing direction. So again, we had 2 horizontal tangent lines, t equals 0 and t equals 2. All right, so those are going to be at the points 0, 0 and 2, negative 4. So I can draw those in. We had 2 vertical tangents at t equals negative 1, 2, negative 4, and negative 2, negative 2. I can draw those in, and there's my vertical. So you notice at that point, 2, negative 2, we had both a horizontal tangent line and a vertical tangent line. All right, example 2. X equals 3 cosine of t, y equals 4 sine of t. Find the first and second derivatives. Okay, first derivative, dy over dt, dx over dt. We're going to take the derivative of y. That's going to be 4 cosine t. We're going to take the derivative of 3 cosine t. That's going to be negative sine, so negative 3 sine t. Wait a minute, we can simplify cosine over sine. That's cotangent. So negative 4/3 cotangent t is our first derivative. All right, find second derivative. So first derivative goes up in the numerator. We're going to take the derivative of that with respect to t. We're going to keep that same denominator, dx over dt, minus 3 sine t. All right, let's take the derivative here. So we're going to have to take the derivative of cotangent. That's going to be negative cosecant squared t. The negative 4/3 over the negative 3 simplified to a positive 4/9. That sine of t on the bottom, we can think of that as 1 over sine t, but again, that's also cosecant, so multiplying that to cosecant squared, we're going to get a cosecant cubed, and the negative times the 4/9 is negative 4/9. So there's our second derivative, negative 4/9 cosecant cubed t. Determine the equation of the tangent line when t is equal to pi over 4. Well, we got to have the slope. We got to put pi into our first derivative. So pi over 4, excuse me, for our t. So negative 4/3 times cotangent of pi over 4, well, that's going to be 1. So our slope's negative 4/3. Then we got to have a point. All right, so we don't have a point. Well, we're going to have to go find x and y with pi over 4. So x equals 3 cosine pi over 4. That's 3 square root of 2 over 2, because the cosine of pi over 4 is radical 2 over 2. And for sine, it's the same thing, radical 2 over 2. So that's 4 radical 2, which we can simplify to 2 radical 2. Use your point slope form. So y minus the 2 radical 2 equals negative 4/3 times x minus the 3 radical 2 over 2. You can distribute in the negative 4/3 and put it into slope-intercept form if that's what you were asked to do. Determine concavity for the graph. Well, this is when your second derivative, all right, if it's positive, it opens up. If it's negative, it's open down for that particular t value. So for pi over 4, well, let's see, cosecant, that's 1 over sine. We already said that's radical 2 over 2. So if I flip that, or wait, that was originally 1 over radical 2. Flip that, that's just radical 2. We're going to cube that. We don't have to cube it because this is already negative. So we know that this now concaves down at pi over 4. All right, is it possible for a plane to curve, to loop around and cross itself? Yep, we already saw that. Show that the curve, but we showed it with a horizontal and vertical tangent. Let's look at this. A different example here. Show that the curve represented by a parametric equation has 2 tangent lines at the point 2, 1. It's just that we don't know if they're horizontal, vertical, or slanted. So x is equal to 2 for the x coordinate. So let's put that in for x, and let's solve this for t. So we'll set it equal to 0. It's quadratic. Factor, solve. We get t equals negative 1 and 2. So the graph definitely crosses itself 2, 1 at 2 different times. So there has to be 2 different tangents there. All right, so now we'll take the first derivative, dy over dt, dx over dt. We're going to take the derivative of y. We're going to get 3t squared minus 3. The derivative of our x equation, 2t minus 1. There's my first derivative. I need the slope of my tangent lines. So let's test the t equals negative 1. We plug that in. We get 0 on the top over negative 3 when I plug in negative 1. So that tells me we have a horizontal tangent line at 2, 1. So that's just going to be the horizontal line y equals 1 because of the y coordinate. And that happens when t equals negative 1. Now when we want to test the 2 for the time, we get 9 over 3 when we plug the 2 into our first derivative. So now we have a slope of 3. So this is a slanted tangent line. So we're going to have to go find we have the point. It's 2, 1. So we got to use our point slope form. Y minus 1 equals 3 times x minus 2 when t is equal to 2. Or we can convert that again into slope-intercept form. Y equals 3x minus 5. Okay? All right, so to build the table for points, if you wanted to graph it, or looking at your calculator's screen version of this, you can see here's our point at 2, 1. That's where it crossed itself. We have a horizontal tangent and a slanted tangent. And I know this graph looks a little weird. I think my window is still in a trig format where this is pi over 2. So I apologize for my screen there. I think I used it from the previous one when I had cosines and sines. Arc length. Okay, here's our theorem. To find our arc length, we have the formula. We're going to integrate from alpha to beta as long as our f prime and g prime are continuous on that closed interval. we can take f prime, or dx over dt, squared plus dy over dt, that's your g prime, and then we'll integrate it with respect to t. So set up the integral that represents the length of the curve, use a calculator to find the length, correct to 4 decimal places. And I can understand why, because it's tough to integrate with these square roots here. Unless you can find something on the table, we'll probably go right to the calculator. So there's our lower bound or upper bound. We just have to find the derivative of x and y. So dx over dt will be 1 plus 1 over 2 square root of t. Then with the minus for the y, we just got to put in a minus. So we'll substitute those into the formula. Like we said, put in our lower bounds 1 and 2. Foiling that out, we'll do a little side work over here. We should probably get our middle terms to cancel because of the plus and the minus in our two binomials. So plus 1 over square root of t, minus 1 square root of t cancel. So 1 plus 1 is 2. 1/4 plus 1/4 is 1/2, so 1 over 2t. All right, so let's go to our calculator and find the value. So I just did this on my home screen with my integral command, and to 4 decimal places is 6, so 8 is going to round the 6 up to a 7. So there's the arc length of that curve. So again, the other thing I want to point out is that the curve is traversed exactly once. That means it can't loop over itself. Area. So here's our area formula. Now, if I have my area is the integral from a to b of y dx. So y is your g of t. So dx would be the derivative of f of t with respect to t. All right. Now, if we had to do it the other way, you could have x here, but then that would be dy, and that would be then f of t times g prime of t. All right. And it doesn't, again, so you switch these boundaries, we're okay. All right. So to find the area enclosed of the curve, boom, we have x equals t squared minus 2t, y is equal to square root of t. There's 1. X equals 0, that's just a vertical line. Now, you can output this in your calculator, especially with parametrics. If you have x sub 2 equal to 0 and y sub 2 equal to t, it's going to graph that red line. It's going to graph the vertical line for you right there. All right, so based on what we see here, we got to find out, where does the parametric curve cross the 0? Well, it looks like we're going to cross at 0, but I'm not sure about this value up here, so let's go find it. So if we're going to go find it when x is equal to 0, we're going to set that equation right here, our first one for x equal to 0, and that's going to be at t and t minus 2 when you factor out the t, 0 and 2. There's my 2 answers. Okay, so again, my y scales are a little goofed up. We might want to adjust those on your calculator. All right, so what are my y values? Well, plug in the 0 for t, we get 0. We'll plug in the 2, we get square root of 2. So we're going to be at 0, 0, and 0, radical 2 for my 2 points. So to find the area, we have to think about this as the right function minus the left function to integrate with respect to y. So we're going to write this as the area equals c to d of x dy. Again, we're integrating with respect to y. So when we integrate this, this will be f of t times g prime of t dt. All right, so enter, whoops, one too many here. Enter this into our integral. So that would be y equals 0 to radical 2. Right function minus left function dy is the same thing if we do this with t. It would be the 0, that's this x function, minus x of t, that's this function right here. Then we multiply it by the derivative of the y equation. All right, so 0 minus x of t, or first, that's going to be a negative, so let's factor that negative out to the front. There's my t squared minus 2t. The derivative of the square root of t, that's 1/2 over, or excuse me, 1 over 2 square root of t, or we can leave it as t to the negative 1/2, which I chose to do because I need to distribute that, which I will do. So that gives me 1/2 t to the 3/2 power minus t to the 1/2 power dt. So let's integrate with respect to t. That's going to give me 1/2 t to the 5/2. Remember, we're adding 1, so that's taking your 5/2 divided by 5/2 is the same as multiplying by its reciprocal 2/5. So the 2's cancel, leaving us 1/5. 1/2 plus 1 is 3/2. Divided by 3/2 is the same as multiplying by 2/3. Well, we can see if we plug in zeros, that's going to give us a 0, so we just have to substitute in the 2. And we do some number crunching here. We get negative, in brackets, 4/5 radical 2 minus 4/3 radical 2. Simplify everything to common denominators. We're going to get a negative 8 over 15, but then multiply the negative to it, so we get a positive 8 over 15 square root of 2, square units, whatever they may be. Okay, that's the end of this video.